In this lesson, we're looking at equations of exponential functions. Specifically, what we're going to try and do is we're going to try and express all exponential functions in this format, which is f of x is equal to a b to the power of x plus c. So we're going to take an exponential function that's been written in the form y is equal to a f of k times x minus d plus c. So this is your general transformations. And we're going to change it all to simply a vertical stretch and a vertical translation. So we're going to incorporate all the transformations into simply a vertical stretch and a vertical translation. So we're going to translate a description also of an exponential function into this form as well. So in the same ways that lines can be written as y is equal to mx plus b, if you look at this, that's your slope-intercept form. If we look at it in terms of a function, well, your x has a vertical stretch factor and a vertical translation. So lines are also functions that have been transformed as well with a vertical stretch and a vertical translation. We can do the same thing with all exponential functions. We can change all exponential functions into the form whereby there's only a vertical stretch and a vertical translation. This means we can always write exponential functions solely in terms of vertical stretches and transformations, and rather translations. Why is this? How are horizontal stretches and translations incorporated into this form? So let's take a look at the first example. Consider y is equal to 3 to the power of 2x. This means that there is a horizontal stretch by a factor of 1/2, and you can say compression, right? Because this is by a factor of 1/2, so that means that the graph is going to get smaller, or is going to be compressed rather. So how do we take this horizontal compression and change this into this form right here where we only have vertical stretches and vertical translations? So if we look at this, y is equal to 3 to the power of 2x. We can write that as y is equal to 3 to the power of 2 times x, because that's what 2x means, quite obviously. If we remember our exponent rules, we can say y is equal to 3 squared to the power of x, because when I have an exponent outside the bracket and an exponent inside the bracket, I should be multiplying them. And then I'll have y is equal to 9 to the power of x. So have I now translated this into the form ax to the power of b plus c? Well, let's just see. Y is equal to a b to the power of x plus c. Do I have a coefficient in front of my 9? No, I don't. That means that a is equal to 1. My base here is equal to 9, and I don't have a vertical translation, so c is equal to 0. So essentially what I've done here with this equation is I've taken something that has a horizontal compression by a factor of 1/2, and I've written it solely in the terms of a vertical stretch by a factor of 1, no vertical translation. I've just changed the base. Let's look at example 1, this next one as well. Consider y is equal to 2 to the power of x plus 3. Well, again, I'm going to have to remember my exponent rules. When do I add exponents? Well, I add exponents when I have a multiplication of the same base, right? So in this case, my base is 2. They're both raised to an exponent, in this case x, in this case 3. So my exponent rules say I should be adding these, right? So y is equal to 2x plus 3. This is the equivalent equation. Well, I can evaluate this because 2 to the power of 3 is a constant. So y, 2 to the power of x, times 8, okay? And I'm going to rearrange this into this format right here. Y is equal to a b to the power of x plus c, so y is equal to 8 times 2x, and then I don't have any term after that. So what I'm going to do now is I'm going to verify that I have put it into a vertical stretch and translation form. So y is equal to a b to the x plus c. Well, if I look at this, my a is 8, my base is 2, and I have no term after here, so my c is simply equal to 0. So yes, I have in fact turned this, which was a horizontal translation, 3 units to the left, I've turned it into this equation and expressed it solely as y to the power of 2 to the, y is equal to 2 to the power of x with a vertical stretch factor of 8. Okay, moving on. So if I look at this, y is equal to 2 to the negative x. Well, remember, if there's a negative in front of the x, that means a reflection in the y-axis. So again, I only want a positive exponent if I'm using this format right here for exponential equations. Again, a vertical stretch and a vertical translation. So how do I change this, which has a negative exponent, into something with a positive exponent? Well, I can think of y is equal to 2 to the power of negative x as this. Y is equal to 2 to the negative 1, then to the power of x, because I should be multiplying these two exponents if you have an exponent outside the bracket and an exponent inside the bracket. And then I can change my base, 1/2 x, because 2 to the negative 1 is simply equal to 1/2. So have I translated it in terms of this format here? Well, my a is 1, my base is 1/2, and I don't have a term here, so c is 0. Okay, if I look at example 2, it says for what value of k would y equal to 3 to the power of kx be equal to the following functions? So I have to find what value of k would make this equal to this. So I'm going to write that statement. Therefore, 3 to the power of kx is equal to 9x. And the trick to this is always to look at, can I express 9 in terms of this base right here? Well, I can. 3 to the power of kx, another way of saying 9 is 3 squared, then x. So that means 3kx is equal to 2x. So this expression right here, or this equation right here, is equal to this function if k is equal to 2. As you can see right here, k and 2. Okay, same format here. I need to equate this with this. So therefore, 3 to the power of kx is equal to 1 over 3 to the power of x. Now, another way of expressing 1 over 3 is 3 to the negative 1 to the power of x. So then 3kx is equal to 3 to the negative x. So what is your value of k that makes these equivalent, or makes these equal? K is equal to negative 1. Last example here, making these two equal to each other. I want you to think of a way of making 1 over 27 similar to 3 to the kx. Okay, so this one's going to be your homework question. So I want you to challenge yourself to re-express this in terms of 3 to the power of something and make it then equal to 3 to the power of kx and find out what your k value is. Okay, looking at example 3, express the following in the form f of x is equal to a b to the power of x plus c. So again, only in terms of a vertical stretch and a vertical translation. So if I look at this function right here, I can see that I've been horizontally translated 3 units to the left, and then a vertical translation of 5 units up. Or rather, 5 units down, since it's negative. So what I'm going to do is I'm going to re-look at this, and I want to get rid of this horizontal translation, 3 units to the left, and I only want to express it in terms of a vertical stretch and a vertical translation. So therefore, f of x is equal to, and remember, if I'm adding my exponents, that means that I have multiplied these two things together. Because they have the same base, therefore I should be adding the exponent. Right? The same base of 2, add the exponents when they multiply. That's just exponent rules. and then I keep the minus 5. 2 to the power of 3 is a constant, that's 8. So f of x is equal to 8 times 2 to the power of x minus 5. And have I put it in this form? Well, I certainly have. This would be your a, your base is b, and your c is negative 5. Okay. Moving down to b, f of x is equal to 4 times 2 to the power of 3x plus 2. So this almost looks like it's already in a vertical stretch, vertical translation form. But as you can see here, I have a horizontal compression by a factor of 1 over 3. So I need to get rid of that horizontal compression factor because, again, I don't want a coefficient in front of my x there. So how can I redo this? Well, we saw this before. F of x is equal to 4 times, and I can bring the 3 inside the bracket because recall, if you have an exponent inside the bracket and an exponent outside the bracket, we would multiply them together, so that would be 3 times x, so 3x, and that's what I have here, plus 2. So I get 4 times 8 to the power of x plus 2, and now I certainly have it in terms of a vertical stretch and a vertical translation. All I've effectively done is I've changed the base of the function from 2, I've changed it to an 8. C and D are homework questions, and we'll end this lesson with example 4. Express the following in the form of f of x is equal to ab to the power of x plus c. So I'm just going to take this description and I'm going to put it in this form right here. So the function f of x is equal to 1/4 to the power of x. So my base is 1/4 and I'm raising it to the power of x. Then I'm taking this function and I'm vertically stretching it by a factor of 3, reflecting it in the y-axis, and then translating it 5 units to the right. So how can I take this function right here and do all these things to it? Well, I'm going to define this new function with all the transformations as g of x. So therefore, g of x vertically stretched by a factor of 3. So that means I take my function, I multiply it by 3. The base of my function was 1/4. But as you can see here, I've got a reflection in the y-axis. That means I need to put a negative in front of my x values. And then translated 5 units to the right. So 5 units to the right means x minus 5. So this right here represents this description. But as you can see, it's not solely in the terms of a vertical stretch and a vertical translation, because right here I've got my reflection in the y-axis and I have my horizontal translation. So I need to get rid of this and change my equation to this. So how do I do that? Well, I'm going to keep this vertical stretch factor and I'm going to rewrite this as 1 over 4. And instead of negative, I'm going to write this times negative 1 times x minus 5. And hopefully that will make this a little clearer. Well, this negative 1 I can apply to the base. And applying a negative exponent to the base, especially a negative 1, will cause you to take the reciprocal. So that means 4. And that gets rid of my negative exponent. And now I simply have x minus 5. Well, remember what we had in the previous examples. If you're adding or subtracting, then what you're doing there is you are multiplying the two numbers with the same base. So 3 times 4 to the power of x times 4 to the negative 5. Because if I multiply these two numbers together, I should be adding these exponents, and x plus negative 5 is x minus 5. But I know that 4 to the negative 5 is simply 1 over 4 to the power of 5. So it's a constant value. And what I'm going to do is, if I'm multiplying here, and I'm multiplying here as well, I'm going to take this and incorporate it into one vertical stretch factor. So 3 to the over 4 to the power of 5 times 4 to the power of x, and that's simply equal to 3 over 1024 times 4 to the power of x. And I have no vertical translation factor because I had no vertical translation over here, just a horizontal translation. Okay, this one is also homework to do. Okay, thanks for watching.